How did early gas thermometers use isochoric processes? Imagine trying to measure how hot or cold something is without touching it. Early scientists used a clever trick involving gases to do just that. They built devices that relied on a principle called the isochoric process. This means keeping the gas inside the thermometer at a fixed volume, so it can't expand or shrink. When the temperature changes, the pressure of the gas shifts instead. In these early thermometers, a sealed glass bulb filled with a specific gas was connected to a pressure-measuring device called a manometer. Since the volume of the gas couldn't change, any increase in temperature made the gas particles move faster, bump into each other more often, and push harder against the walls of the bulb. This caused the pressure inside to rise. Conversely, when it cooled down, the pressure dropped. The key to understanding how these thermometers worked is the ideal gas law. It states that pressure times volume equals the number of gas particles times the gas constant times temperature. Because the volume was fixed, the pressure was directly proportional to the temperature. So, by measuring the pressure, scientists could determine the temperature accurately. The pressure changes caused the liquid in the manometer to move up or down. When the pressure increased, the liquid level would rise, and when it decreased, the liquid would fall. These movements were calibrated to correspond to specific temperature readings. This made the device a reliable tool for measuring temperature before electronic sensors existed. Since no work was done by the gas during these processes, because the volume didn't change, the internal energy of the gas only changed with heat. When the temperature went up, the internal energy increased, and when it cooled, it decreased. This simple setup allowed early scientists to understand and measure temperature in a straightforward way. In essence, early gas thermometers used the isochoric process by keeping the gas volume constant and measuring the pressure changes. These pressure readings directly told us how hot or cold something was, making the principle both practical and precise. This approach helped lay the foundation for modern temperature measurement techniques based on thermodynamics.